Good evening, everybody. Today we will discuss the nucleophilicity and basicity. So, what do you mean by a nucleophile? A nucleophile means a species which donate a pair of electron to an atom other than hydrogen. For example, OH minus ion donate a pair of electron to the carbon, and this reaction is a irreversible reaction. So the rate of a reaction, the strength of the nucleophilicity is determined on the basis of the rate of a reaction. And what do you mean by a base? A base means which donate a pair of electron to the atom. See in this example, ammonia donate a pair of electron to the hydrogen. Okay, so we will get NH4 plus as the final product. So finally, the base means, basicity means it is a subset of the nucleophile, and base it is always a nucleophile, but it only attacks the hydrogen. But nucleophilicity means it is a nucleophile attack any atom other than hydrogen. So in definition, basicity is measure of how readily a atom donates its electron to a proton, and it is characterized by a reversible reaction. That means it exists in an equilibrium. So the acid-base reaction and making it a thermodynamic property. Whereas in nucleophilicity is a measure of how readily a atom donate its electron pair to other atom, and it is characterized by a rate constant K, and it is a kinetic property. Now we are moving into the some of the example. So first one, Cl minus, Br minus, iodine minus, Hs minus, Rs minus, etc. They are only a nucleophile. That means Hs minus can attack a carbon because the sulfur and the atomic size of the sulfur and the carbon are of the same size and comparable one, but it cannot attack a H plus because the hydrogen is a very small atom and it have only one s orbital, and if it overlap with the hydrogen, that means H plus ion, the overlapping is not at all effective. That's why these first category are belonging to the nucleophile only. They are not a base. The second category, they are acting as only base. For example, if we consider the H minus, it can combine with the H plus ion and to form the hydrogen gas. That's why it is acting as a base. But it is not a nucleophile because H plus ion, H minus ion cannot combine with the carbon because the size of the carbon and hydrogen are entirely different. So the overlapping between the 1s orbital of the hydrogen and p orbital of the carbon is not at all effective. That's why this category is only a base. They are not act as a nucleophile. So next category is the strong base, at the same time it is a strong nucleophile. See the first example, OH minus ion. The OH minus ion can attack the carbon because they are approximately similar in size. Similarly, OH minus ion can attack H plus ions. That's why the OH minus ion acts as a strong nucleophile, at the same time it is a strong base. Next category is they are strong nucleophile and they are weak nucleophile, at the same time they are act as a weak base. Example, water. So it cannot donate the pair of electron from the oxygen readily. That's why it acts as a weak base. Similarly, it cannot donate its pair of electron to H plus very readily. That's why it is acting as a weak base. So the water is acting as a weak nucleophile and weak base, and OH minus acting as a strong nucleophile and strong base, whereas H minus act as a base only and HS minus act as a nucleophile only. Now we are moving into some of the factors or general characteristic of the basicity and nucleophilicity while we are discussing the periodic table. See, in the periodic table, we can see the nitrogen, carbon, oxygen and fluorine. They are belonging to the first period. So, as we move from the right to left, that means from fluorine to carbon, the nucleophilicity enhances. That means as the electronegativity of the atom increases, the nucleophilicity and basicity both are decreasing. So the best nucleophile in the first four, carbon, nitrogen, oxygen and fluorine, is the carbon. And if we compare a group, see here, if we compare a group, the fluorine, chlorine, bromine, iodine in the halogen family, we can see that every one are strong base and strong nucleophile without any solvent. Now, if we apply a protic solvent, what will happen? If we apply a protic solvent, the nucleophilicity at the same time basicity enhances. This is because consider the lower side of this slide, in which fluorine F minus is a smaller in size and iodine I minus is bigger in size. Since we are using the protic solvent, there is no interaction between the F minus and iodine minus. That's why its nucleophilicity and basicity retain as such. That's why the F minus is a good basic and nucleophilic in nature. Whereas if we apply a protic solvents, what will happen? The solvent layer is, the F minus ion is surrounded by the polar protic solvents. Okay, so that's why it has the donating capacity of the F minus ion decreases. So that's why if we apply a protic solvents, what will happen? When we come down to the group, the nucleophilicity is decreases. Okay. Now I am just repeating the nucleophilicity and basicity in polar protic and aprotic solvent. So in first case there is no solvent, so the nucleophilicity and basicity increases from bottom to top. Whereas in polar protic solvents, you can see that a layer of the solvent is surrounded by the anion. So that's why its tendency to donate pair of electron decreases. So they are acting as a strong base, but they are not a good nucleophile. Whereas in the polar aprotic solvent, there is no interaction between the ion and the solvent layer. So that's why they are a strong base, at the same time they are a strong nucleophile. Thank you.